Hello friends, and welcome to CNN Cleaning's Cleaning Chemical class. In the last video, we began a series on pH. If you haven't watched it, I'd suggest backing up and checking it out first, because we're going to build heavily on those principles in this video. If you have watched it, then on to the chemistry. In the last video, we finished up by talking about the pH scale, and how by adding hydrogen ions to a solution, we would be shifting the balance of the solution towards the acidic end, and if we add hydroxide molecules, we'd be shifting it back to the alkaline end. Let's dig a little deeper into that relationship in this video. Many acids and bases are really clear-cut in their relationship, and we call those strong acids and strong bases. These can usually be spotted because they'll have a clear hydrogen or hydroxide group in their chemical formula, and when added to water, they dissociate completely. For example, let's look at a common strong acid, hydrochloric acid, or HCl. When hydrochloric acid is dissolved into an aqueous solution, the result is hydrogen ions and chlorine ions. Both of these are separated in the solution and won't come back together. When this is added to a solution, the hydrogen ions begin tipping the balance towards an acidic solution, and the amount of hydrochloric acid added has a direct relationship to the pH of the solution. On the other side, a comparable strong base would be one we've talked about in the degreaser video previously, Li, sodium hydroxide. When sodium hydroxide is added to an aqueous solution, it also dissociates, forming hydroxide molecules and sodium ions. So what would happen if we add a strong acid to a strong base? When a strong acid and a strong base react, the hydrogen and hydroxide molecules form water, and the other particles, which take no part of the reaction, would join as a salt. In our example of sodium hydroxide and hydrochloric acid, adding hydrochloric acid to a solution of sodium hydroxide would form water, heat, and table salt, sodium chloride. Neutralization is always an exothermic reaction, which means as you add hydrochloric acid, the solution is going to produce heat, and it can produce a lot of it very quickly. As the balance of hydroxide and hydrogen approaches, the solution would approach a pH of 7. If you were to keep adding hydrochloric acid, the solution would then pass equilibrium and the pH would continue to lower to the acidic range. Strong bases are generally easy to identify. All of the common strong bases contain a hydroxide combined with an alkali metal or an alkali earth metal. The most common examples are sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, and cesium hydroxide. Depending on who's counting, there are either 6 or 7 strong acids. You'll notice these will contain at least one hydrogen, but they are a little more difficult to spot than the bases. We've already talked about hydrochloric acid. There's also nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, perchloric acid, and sometimes, depending on your chemistry professor, chloric acid. These strong acids and bases are cool and all, but as you can maybe tell from their name, they tend to gravitate towards the outer edges of the pH scale. Some of them can be quite useful for cleaning, like sodium hydroxide, which we talked about in the degreaser video, or hydrochloric acid, which is used in some commercial rust removers and toilet bowl cleaners. But most of our regularly used cleaning chemicals make use of milder components, weak acids and weak bases. Unlike strong acids and bases, weak acids and bases don't completely disassociate in solution. There are some different molecules still in existence, and not all the hydrogen or hydroxide is available. These weak acids and weak bases are more useful to us as cleaners, and they are deserving of their own video, so we'll get into more detail on them next time. And until then, thanks for watching.